China is building something absolutely insane. The most unbelievable ideas are turning into reality, and the future is taking shape in front of our eyes. From deep below the water to high above the clouds, these are some of China's greatest creations. Don't miss out as we bring you the unbelievable world of China's megabridges. We start with a bridge whose deck floats 625 meters above the river below. A bridge built at heights so extreme that construction workers needed to undergo psychological evaluation before they were allowed on site. It's taller than China's tallest building, the Shanghai Tower, and equivalent to stacking 2 Eiffel Towers end to end. The deck is so high that if you dropped a rock from the top, it would fall for approximately 11 seconds before hitting the water. Built in southwestern China over the Beipan River, Huajiang Canyon Bridge is now the highest bridge in the world. The bridge is also set to become the longest spanning mountain bridge in the world, with a total length of 2,890 meters. The Huajiang Canyon Bridge employs a cable-stayed design where the deck hangs from cables connected to tall towers. Unlike suspension bridges where cables drape between towers and the deck hangs from vertical suspenders, cable-stayed bridges use cables that run diagonally from the towers directly to the deck, creating a distinctive fan or harp-like appearance. This design offers several advantages for the extreme conditions at Huajiang. Cable-stayed bridges are more rigid than suspension bridges, making them better at handling the constant traffic loads while resisting wind-induced movement. They're also more efficient for medium-length spans, like Huajiang Bridge's 1,000-meter main span. The towers themselves rise approximately 300 meters above the deck, meaning the absolute highest points of the bridge structure soar nearly 925 meters above the river, taller than the tallest building in most cities, perched on the edge of a mountain plateau. The construction timeline for the Huajiang Canyon Bridge began in 2019, with completion scheduled for 2025, representing a 6-year marathon of engineering precision in one of the most hostile construction environments imaginable. However, turning the idea of such an extreme bridge into reality was not easy. Building at these heights introduces challenges that don't exist for normal bridges. The first problem is wind. At 625 meters above a river valley, wind speeds can exceed 200 kilometers per hour during storms. The bridge had to be designed to handle not just the pressure of wind pushing against its surface, but also the complex aerodynamic effects that can cause catastrophic oscillations. Engineers conducted extensive wind tunnel testing using scale models of the bridge, subjecting them to simulated typhoons and mountain wind patterns. To counter these winds, workers had to anchor the bridge towers deep into the mountainside to handle the enormous forces from the suspended deck. The second challenge was getting materials to the construction site. The bridge location is so remote and the terrain so hostile that conventional construction equipment couldn't reach it. Engineers had to build temporary access roads carved into cliff faces, sometimes with clearances so tight that trucks could only pass within centimeters of the edge. Some equipment had to be airlifted by helicopter, adding millions to the construction budget. Despite its apparent grandeur, the bridge has a much more practical purpose. Before this bridge, communities on opposite sides of the canyon were separated by a journey that could take half a day through winding mountain roads. Once completed, the Huajiang Canyon Bridge will reduce this to less than 3 minutes. The bridge is part of the Pu'an to Panzhou Expressway, connecting multiple provinces across southwestern China. For approximately 300,000 people living in the surrounding counties, this means agricultural products can reach urban markets faster, students can access better schools, and medical facilities become available to the entire region. It's because of these far-reaching economic benefits that China has invested $500 million into the project. Despite the construction challenges, China's Guizhou province has become the unexpected capital of high-altitude bridge engineering. The province is home to dozens of the world's 100 highest bridges, transforming what was once a barrier into a testing ground for China's bridge engineering capabilities. But this recently opened structure isn't the only behemoth in the province. In fact, the Huajiang Canyon Bridge took the title of the highest bridge in the world from another soaring structure just 200 kilometers away. It is the Beipan Bridge. also known as the Doog Bridge, which lies 565 meters above the water and was just as complex to build. Before the Canyon Bridge, there was the Doog Bridge, which made history by becoming the first structure in the world to surpass the 500-meter height barrier many engineers thought was impossible. Standing 565 meters above the Beipan River, it was the world's highest bridge from its opening in 2016 until 2025. The bridge deck sits higher above the ground than the Sears Tower is tall. Here, we can make an important distinction between the tallest and the highest when it comes to megabridges. A bridge's height is the maximum vertical distance between the ground and the bridge deck. Meanwhile, the tallest bridge refers to the height of the structure itself, starting from the base of the towers that hold it. That title still belongs to the Millau Viaduct in France, which is 343 meters tall. Before China's decision to build the Doog Bridge, engineers had for decades debated whether building a bridge at this height was even feasible. The extreme winds, the difficulty of construction, and the sheer engineering challenges seemed insurmountable. However, Dugan represents a fundamental shift in high bridge engineering, proving that cable-stayed designs could handle the most extreme conditions. The Doog Bridge is part of the G56 Hangzhou-Rili Expressway, a massive 4-lane highway that stretches an incredible 2,935 kilometers from Hangzhou near Shanghai, all the way to the border of Myanmar near Tibet. This expressway crosses some of the most challenging terrain on Earth, requiring multiple record-breaking bridges along its route. The bridge connects Xuanwei City in Yunnan Province to Shucheng County in Guizhou Province. Before the bridge opened, the journey between these two cities took 4 to 5 hours of winding through mountain roads. The Doog Bridge reduced that journey to just over 1 hour, transforming transportation in the region. The bridge uses a cable-stayed design, where the deck is supported directly by cables connected to towers. The structure has a total length of 1,341 meters, with a main span of 720 meters stretching across the deepest part of the valley. The deck is made of a steel truss, a framework of interconnected steel beams that provides strength while keeping the weight manageable. The two towers are H-shaped and stand among the 30 tallest bridge towers in the world. The eastern tower measures 269 meters tall, while the western tower reaches 247 meters. Together, they support 112 pairs of stay cables arranged in a fan shape, each one precisely tensioned to distribute the load evenly across the structure. Construction began in 2011, but the project faced unique challenges from the start. The region's landscape is dominated by karst formations, limestone that has been eroded over millions of years, creating caves, sinkholes, and unstable rock. Engineers had to repeatedly move the planned location of the bridge higher and higher on the mountainside to avoid underground caves and areas where the rock was cracking or unstable. The Beipan River Valley itself posed another problem. The gorge is so deep and the cliffs so steep that the river below is almost never directly illuminated by sunlight. This created severe temperature variations and wind patterns that engineers had to account for in the design. Wind was one of the most serious concerns. At 565 meters above the valley floor, the bridge deck often sits above the clouds and fog. Wind speeds at this altitude can be extreme, and engineers had to ensure the bridge wouldn't develop dangerous oscillations like those that destroyed the famous Tacoma Narrows Bridge in 1940. To test the design, engineers built scale models and subjected them to wind tunnel testing that simulated the specific conditions of the Beipan River Valley. The aerodynamic shape of the steel truss deck was carefully refined to allow wind to pass through, rather than creating lifting forces or vibrations. The construction timeline stretched from 2011 to September 2016, when the bridge was finally completed. Workers had to build temporary access roads carved into the cliff faces just to reach the construction site. Just like the Canyon Bridge, some equipment and materials had to be transported by helicopter due to the extreme terrain. The bridge foundations required drilling deep into the mountainside bedrock. The tower foundations use group pile systems, clusters of concrete piles drilled dozens of meters into solid rock to anchor the massive towers against the forces generated by the suspended deck. Stringing the cables across the 720-meter main span was one of the most challenging phases. Workers used pilot cables, thin ropes shot across the gap, to pull progressively thicker cables until they could transport the main structural cables into position. The precision required was extraordinary, as even small errors in cable tension would create a wavy deck surface. The Doge Bridge officially opened to traffic on December 29, 2016. The total cost was approximately $144 million, a relatively modest sum for a structure of this scale and ambition. For its epic design, in 2018, the bridge won the Gustav Lindenthal Gold Medal at the 35th International Bridge Conference, often called the Nobel Prize of Bridge Construction. The same year, Guinness World Records officially certified it as the world's highest bridge, cementing its place in engineering history. Innovations used in building the Doge Bridge have been used in subsequent bridge projects across China and around the world. The Doge Bridge is more than just a record-breaking structure. It's part of China's strategy to develop its western provinces, which have historically been isolated by mountainous terrain. The Beipan River Valley had been a barrier to transportation for thousands of years. The bridge erased that barrier in a single span. With this structure, China welcomed a revolution in engineering. In 1994, the country had just one bridge, over 122 meters tall. Today, the western provinces of Guizhou, Yunnan, Sichuan, and Hubei contain over 50 bridges exceeding 150 meters in height, including 10 of the world's 12 highest bridges. The Doge Bridge held the title of world's highest bridge for 9 years, before being surpassed by the Huajiang Canyon Bridge. However, the Doge Bridge's significance extends beyond its height record. It proved that cable-stayed bridges could handle the most extreme high-altitude conditions. It demonstrated that the 500-meter barrier could be broken, and it showed that even China's most remote and challenging terrain could be connected by modern infrastructure. The bridge remains a popular tourist destination, with observation decks at either end offering stunning views of the surrounding mountains and valleys. Photographers and engineering enthusiasts travel from around the world to experience the structure that seems to float above the clouds, connecting two provinces that were once separated by an impassable gorge. But it's only number 9 on our list, and the bridges ahead will push boundaries even further. Changtai Yangtze River Bridge. Moving east to Jiangsu Province, we arrive at a bridge that opened to traffic in September 2025 and immediately claimed multiple world records. The Changtai Yangtze River Bridge isn't just breaking one record, it's setting the standard for an entirely new category of infrastructure. The bridge stretches 10.3 kilometers across the Yangtze River, connecting the cities of Changzhou and Taizhou. Its main span measures 1,208 meters, making it the longest cable-stayed bridge in the world, surpassing the previous record holder, Russia's Russky Bridge, which has a main span of 1,104 meters. But length is only part of the story. What makes the Changtai Bridge truly revolutionary is that it's the first bridge on the Yangtze River to combine 3 different transportation systems in a single structure: an expressway for vehicles, a regular local road, and an intercity railway. This triple-function design represents a fundamental rethinking of how bridges can serve multiple purposes simultaneously. The journey between Changzhou and Taizhou used to take 80 minutes by road, winding around the Yangtze River. The Changtai Bridge reduces that journey to just 20 minutes. For the millions of people living in the Yangtze River Delta, one of China's most economically dynamic regions, this time, savings translates directly into increased productivity and economic opportunity. Construction of the bridge took 6 years, from 2019 to 2025, and required solving engineering problems that had never been encountered before. The total length of the road and rail section alone spans 5.3 kilometers, setting another world record for the largest continuous-length steel truss bridge. The bridge consists of several sections. The main cable-stayed section has that record-breaking 1,208-meter span over the primary navigation channel. 2 steel truss arch bridges, each with a 388-meter span, handle dedicated navigation channels. and a continuous steel truss bridge with three 124-meter spans covers non-navigable sections. Together, these components create a seamless crossing of one of the world's busiest waterways. The bridge towers rise 350 meters into the sky, roughly equivalent to a 120-story building. They're designed in a distinctive diamond shape and constructed from a combination of steel and concrete. This hybrid approach provides the stability needed to support the massive loads, while maintaining enough flexibility to handle temperature changes that can cause steel to expand and contract. The most innovative aspect of the Tian'e Bridge is its asymmetrical lower deck design. Traditionally, engineers place the heavier railway in the center of the bridge with roads on either side. This balanced design distributes the weight evenly and simplifies the engineering. But in urban areas, this standard layout wastes valuable land because roadways often need to curve to connect to the city's network. The Tian'e Bridge takes a different approach. On one side of the lower deck runs a high-speed railway capable of speeds up to 200 kilometers per hour. On the other side is a regular local road. This side-by-side arrangement saves land and provides more direct connections to the existing transportation networks in both cities. But this design created enormous engineering challenges. Railway sections can weigh up to 3 times as much as road sections. Placing all that weight on one side of the bridge creates uneven loading on the support cables, which could cause the deck to tilt or develop structural problems over time. The solution required extraordinary precision. Engineers, led by Qin Shunquan, chief scientist of the China Railway Group, had to carefully adjust the tension in each of the hundreds of cables supporting the railway side to keep the deck perfectly level. But adjusting the cable tension shifted the structure itself, misaligning its center line. The team had to develop computer models that could predict these effects and calculate the exact adjustments needed to keep everything aligned while under construction. The final connection of the main span required millimeter-level precision. When the two sides of the bridge met in the middle, the alignment had to be within 2 millimeters, less than the thickness of a coin. To achieve this, the construction team developed an intelligent decision-making system that monitored temperature, wind, and structural stress in real time, making constant micro-adjustments to keep everything aligned. The foundations of the bridge presented their own challenges. The Yangtze River at this location has powerful currents that constantly erode the riverbed. Engineers had to design and build massive underwater caisson foundations, essentially giant concrete boxes sunk to the riverbed and filled with concrete to create stable anchoring points for the towers. The project team set a new world record for the fastest sinking of a large caisson in a silty clay layer. They developed an intelligent airlift excavation system that could remove sediment from inside the caisson while it was being lowered, allowing for faster and more controlled sinking than traditional methods. Moving the massive steel truss segments into position required specially developed equipment. The team built the world's largest bridge deck crane, with a lifting capacity exceeding 10,000 ton-meters. This enormous machine could position bridge segments weighing hundreds of tons with millimeter-level accuracy, essential for maintaining the alignment of the entire structure. The stay cables themselves are engineering marvels. Some of them are exceptionally long and heavy, designed to handle not just the static weight of the bridge deck, but also the dynamic loads from trains traveling at 200 kilometers per hour and the constant traffic of vehicles. Each cable had to be precisely manufactured, transported to the site, and installed with exact tension specifications. Li Zhen, the project's chief engineer for the Jiangsu Transport Department, explained that the foundations were reinforced with extra strength specifically to resist the powerful currents of the Yangtze. The river flows 6,300 kilometers from the Tibetan Plateau to the East China Sea near Shanghai, making it Asia's longest river and the world's third longest. At this location, the current is strong enough to shift sediment and create significant lateral forces on the bridge foundations. The Tian'e Bridge also incorporates cutting-edge technology in other ways. Engineers developed a satellite-guided tower crane system that used GPS positioning to place materials with high precision during construction. They built intelligent monitoring systems that continuously track the structural health of the bridge, measuring everything from cable tension to concrete stress to wind-induced vibrations. Officials say the bridge will significantly enhance connectivity and economic activity in the Yangtze River Delta. The region is already one of China's most important economic zones, home to major cities like Shanghai, Nanjing, and Hangzhou. The Tian'e Bridge adds another critical link in the transportation network that ties these cities together. The bridge's completion in 2025 marks another milestone in China's systematic approach to building record-breaking infrastructure. Before the Tian'e Bridge, the Ruski Bridge in Vladivostok, Russia, held the cable-stayed span record at 1,104 meters since its completion in 2012. The Tian'e Bridge extends that record by 104 meters, a jump of nearly 10%. This pattern repeats across China's bridge-building program. 6 of the 10 longest cable-stayed bridges in the world now span the Yangtze River, and all of them were built in the last 20 years. China isn't just building bridges, they're systematically pushing each bridge category to its limits and then finding ways to go even further. At 1,208 meters, the Tian'e Yangtze River Bridge represents the current pinnacle of cable-stayed bridge design, but it's only number 8 on our list, and the bridges ahead will demonstrate even more ambitious engineering. Just downstream from the Tian'e Bridge, another record-breaking structure is taking shape. When the Zhangjiangao Yangtze River Bridge is completed in 2028, it will set 6 world records and become the longest suspension bridge ever built. The bridge will connect 3 cities, Zhangjiagang, Jingjiang, and Rugao in Jiangsu Province. With a river-spanning length of 7,900 meters and a main span of 2,300 meters, it will surpass Turkey's Çanakkale Bridge, currently the world's longest suspension bridge with a main span of 2,023 meters by a full 277 meters. That 2,300-meter main span represents something historic. China will become the first country to break the 2,000-meter barrier for suspension bridges, achieving a span that many engineers considered impossible just a decade ago. Suspension bridges work differently from cable-stayed bridges. Instead of cables running directly from towers to the deck, suspension bridges feature a deck that hangs from vertical suspender cables. These suspenders connect to main cables that drape in a graceful curve between the towers and are anchored deep into the ground on either end of the bridge. This design allows suspension bridges to span much longer distances than cable-stayed bridges, but it also makes them more flexible and more susceptible to wind-induced vibrations. The longer the span, the more these challenges multiply. The first section of the bridge's main tower was hoisted into place in February 2024, marking the beginning of construction on what will become the world's highest suspension bridge tower. When completed, the towers will reach 350 meters into the sky, equivalent to a 125-story building. That's taller than most skyscrapers, and roughly the same height as the Zifeng Tower in Nanjing, Jiangsu's tallest building. These towers aren't just tall, they're also revolutionary in their construction. The Zhangjiangao Bridge will be the first in the world to use a composite structure of steel box and concrete-filled steel tubes for the towers. Traditional suspension bridge towers are typically built entirely from concrete or entirely from steel. The hybrid approach combines the compressive strength of concrete with the tensile strength of steel, creating towers that are both lighter and stronger than conventional designs. This weight reduction is critical for a bridge of this scale. Lighter towers mean less load on the foundations, which translates to lower construction costs and faster build times. The composite design also provides better flexibility to handle thermal expansion and contraction, essential for a structure that will experience temperature variations of 50 degrees Celsius or more between winter and summer. The construction process for the towers demonstrates the precision required for modern megabridges. Each tower segment weighs hundreds of tons and must be positioned with an accuracy of just 3 millimeters across 3 spatial dimensions. To achieve this, the construction team uses a 15,000-ton-meter tower crane combined with digital twin technology, a computer model that mirrors every aspect of the physical structure in real time. By September 2025, the North Tower of the South Navigation Span had surpassed 300 meters in height. Workers installed the T26 segment, which weighs 254 metric tons and stands 13.5 meters tall at an altitude of 300 meters above the Yangtze River. The precision required at this height is extraordinary. Even small errors can compound as the tower grows taller. The foundation work for these massive towers required driving piles 97 meters long into the riverbed. Each pile is essentially a giant concrete column that anchors the tower to bedrock beneath the sediment of the Yangtze River. The south main tower base is designed in an octagonal shape with an area equivalent to 10 basketball courts. Workers poured 37,000 cubic meters of high-strength concrete just for the foundation, enough to fill 15 Olympic swimming pools. The main cables of the Zhangjiangao Bridge will be the longest and strongest ever manufactured for a suspension bridge. Made from galvanized aluminum alloy high-strength steel wires, each cable consists of 247 strands with 127 wires per strand, each wire measuring 5.65 millimeters in diameter. The tensile strength of the steel is 2,200 megapascals, strong enough to support enormous loads while remaining flexible enough to handle the dynamic forces from wind and traffic. The bridge will have 184 pairs of hangers, the vertical cables that connect the main cable to the deck, spaced 16 meters apart along the entire length of the structure. Each hanger must be precisely manufactured and installed to ensure even load distribution across the deck. One of the most innovative features is the self-balancing structure system for the main cable. In traditional suspension bridges, the weight of the deck on one side of the tower must be balanced by the weight on the other side, creating complex engineering challenges during construction. The Zhangjiangao Bridge uses a new system that allows the cables to balance themselves, simplifying construction and improving structural efficiency. The bridge will also feature super large-scale support transformation structure, composite ground anchor foundations. These massive concrete structures, buried deep in the ground at either end of the bridge, anchor the main cables and must resist pulling forces equivalent to the weight of hundreds of thousands of tons. The anchors are so large, they require developing entirely new construction techniques. The saddle structures, the curved supports where the main cables pass over the tops of the towers, will be the largest ever built for a suspension bridge. These saddles are prefabricated in sections and assembled on site, a first for structures of this scale. Each saddle must be machined to microscopic tolerances to prevent the cables from wearing or shifting over time. The entire bridge incorporates an integrated intelligent anti-corrosion system, another world first. The Yangtze River environment is humid and salty, creating ideal conditions for steel to rust. The anti-corrosion system uses sensors throughout the bridge to monitor moisture levels, temperature, and the chemical composition of the atmosphere, automatically adjusting protective measures to prevent deterioration. Construction on the Zhangjiangao Bridge began in 2023, with completion scheduled for June 2028. The total investment is approximately 31.167 billion yuan, making it one of the most expensive infrastructure projects in China. The bridge deck will carry two-way 8-lane expressway traffic with a design speed of 100 kilometers per hour. When complete, the bridge won't just be a transportation link. It will fundamentally reshape the economic geography of central and southern Jiangsu province. The three cities it connects have historically been separated by the Yangtze, with ferry services and roundabout road routes limiting economic integration. The bridge will enable the kind of daily commuting and business interaction that drives modern economic growth. The 6 world records the Zhangjiangao Bridge will set include the longest suspension bridge span, the tallest suspension bridge tower, the longest high-strength main cable, the largest composite ground anchor foundation, the largest continuous-length steel box girder, and the largest displacement expansion device. These records aren't just about bragging rights. Each one represents a genuine breakthrough in engineering capability. Chinese engineers and officials describe the Zhangjiangao Yangtze River Bridge as a landmark project for Jiangsu Province, a representative project for China's bridge technology innovation, and a milestone project for the construction of super-large span suspension bridges. It demonstrates the innovative achievements of continuous exploration and breakthroughs in Chinese bridge construction. At 2,300 meters, the Zhangjiangao Bridge main span is 900 meters longer than the Nanjing-Qiqiaoshan Yangtze River Bridge, itself a record breaker when it opened. The jump from 2,023 meters to 2,300 meters might seem modest, but at this scale, every additional meter of span creates exponentially more difficult engineering challenges. The bridge is only number 7 on our list, but it's already pushing the boundaries of what's considered physically possible for suspension bridge construction. The structures ahead will demonstrate that China's bridge-building ambitions extend even beyond breaking the 2,000-meter barrier. While the Zhangjiangao Bridge soars high above the Yangtze River on the world's tallest towers, our next megaproject takes an entirely different approach. The Shenzhen-Zhongshan link doesn't just cross water, it dives beneath it, disappearing into one of the most ambitious underwater tunnels ever constructed. The Shenzhen-Zhongshan link opened to traffic on June 30, 2024, after 7 years of construction that pushed engineering to its limits. This isn't a simple bridge. It's a 24-kilometer cross-sea passage that combines 2 bridges, 2 artificial islands, and a massive underwater tunnel to connect the technology hub of Shenzhen to the industrial city of Zhongshan across the Pearl River estuary in Guangdong province. Before this link opened, traveling between Shenzhen and Zhongshan required a 2-hour journey winding around the Pearl River. The new crossing reduces that to just 30 minutes, fundamentally transforming transportation in the Guangdong-Hong Kong-Macau Greater Bay Area, one of the most economically dynamic regions in the world. The project cost approximately $4.83 billion and represents one of the most complex cross-sea construction projects ever attempted. It sits about 32 kilometers north of the Hong Kong-Zhuhai-Macau Bridge and 27 kilometers downriver from the Human Bridge, creating a network of crossings that stitch together the cities on both sides of the Pearl River estuary. What makes this project particularly remarkable is that it combines 3 completely different types of infrastructure in a single crossing. The journey starts with the Shenzhen-Zhongshan Bridge, a massive suspension bridge with a main span of 1,666 meters and towers reaching 270 meters high, equivalent to a 90-story building. This section provides a navigation clearance of 76.5 meters, the highest for any sea bridge in the world, allowing even the largest cargo ships to pass beneath. The suspension bridge then connects to an artificial island in the middle of the Pearl River estuary. This island is 625 meters long and 456 meters at its widest point, with a total area of 137,000 square meters, equivalent to 19 international standard football fields. Building this island required solving problems that had never been encountered at this scale before. The Pearl River estuary has water depths of over 40 meters in some areas, with a seabed consisting of thick layers of soft mud interspersed with hard soil layers. Traditional island construction methods wouldn't work. Engineers developed a technique using 57 giant steel cylinders, each 28 meters in diameter, roughly the size of a basketball court. These cylinders were prefabricated in factories, transported to the site, and driven deep into the seabed using specialized equipment. But the hard soil layers beneath the mud presented a challenge. The team developed a deep slurry mixing technology that used a special ship to penetrate the hard layers like a giant blender, mixing in materials to soften the soil and allow the cylinders to be positioned accurately. Once the cylinders formed a ring around the perimeter of the island, ships pumped millions of cubic meters of sand into the center, causing land to emerge from the sea in a kite-like shape. From the western artificial island, the crossing transforms into an underwater tunnel. This isn't just any tunnel, it's the world's longest and widest underwater steel shell concrete immersed tube tunnel, stretching 6.8 kilometers beneath the Pearl River. The tunnel consists of 32 massive prefabricated sections, each weighing 80,000 tons, plus a final joint section connecting them all. Each tunnel section is essentially a giant steel box filled with concrete. Manufacturing these required building a specialized smart factory in Zhuhai that took 10 months to upgrade. The factory produced 23 tunnel sections, patenting 11 inventions in the process. The The sections are 180 meters long, making them the largest tunnel segments ever manufactured for an immersed tube tunnel. Getting these enormous sections into position required developing entirely new equipment. Engineers built the Yihang Jinan 1, the world's first integrated self-propelled transport and installation vessel for immersed tubes. This 20,000-ton ship can carry tunnel sections over 50 kilometers of open water and position them on the seabed with millimeter precision. The installation process is extraordinarily complex. Each section had to be floated to the construction site, carefully ballasted to achieve neutral buoyancy, then slowly lowered 40 meters to the seabed where it connects to the previous section. The precision required is incredible. If the sections don't align within a few millimeters, the tunnel won't seal properly and water will leak in. To achieve this precision, engineers introduced the Beidou satellite navigation system for the first time in cross-sea tunnel construction. The satellite system provides real-time positioning accurate to within centimeters, allowing the installation vessel to adjust its position continuously as it lowers each massive tunnel section into place. The entire floating installation of a single section takes about 10 hours. The tunnel itself is an engineering marvel of safety systems. 14 robots constantly patrol the 6.8-kilometer length, monitoring pipes and cables, detecting potential problems, and even managing traffic during accidents. The robots can direct vehicles using built-in loudspeakers and film incidents while transmitting video to a remote control center. The lighting system inside the tunnel is particularly innovative. Under normal conditions, the walls glow green, but during emergencies, they turn red. The system can also create a progressive color change from yellow to green, guiding people toward exits during evacuations. Intelligent lighting control adjusts brightness automatically based on traffic conditions and time of day, reducing driver fatigue during the underwater journey. Fire safety was a critical concern for a tunnel this long beneath the water. Engineers developed a horizontal smoke exhaust system at the top of the tunnel that improves smoke evacuation efficiency by 42% compared to traditional systems. The tunnel also features dual wavelength flame detectors and an advanced firefighting system designed specifically for ultra-wide underwater tunnels with interchange sections. After emerging from the tunnel at another artificial island, the crossing continues with the Zhongshan Bridge, a cable-stayed structure that uses a different design than the suspension bridge on the other end. The cable-stayed section transitions smoothly to the mainland through carefully designed approach roads. The bridge deck itself uses specialized materials. The steel surfaces are coated with hot-mix epoxy asphalt that's flexible enough to accommodate the movement of steel in changing temperatures, yet strong enough to withstand heavy truck traffic. Inside the tunnel, the pavement uses fire-resistant asphalt as an additional safety measure. The Shenzhen-Zhongshan link officially claims 10 world records, though many of them are highly specific. They include the largest span for a fully offshore steel box girder suspension bridge, the highest navigable clearance for a sea bridge, the largest offshore suspension bridge anchorage, the world's longest and widest underwater steel shell concrete immersed tube tunnel, the largest single-volume concrete pour for a steel shell immersed tube section, the world's first underwater expressway interchange, and the widest repeatedly foldable M-shaped water stop used in an immersed tube tunnel final joint. In April 2024, before the link even opened, the Shenzhen-Zhongshan Bridge won the George S. Richardson Medal at the International Bridge Conference, often called the Nobel Prize of Bridge Engineering. This recognition came for the bridge's excellent quality and innovative construction techniques. Since opening in June 2024, the link has been enormously popular. In the first month of operation, more than 3 million vehicle crossings were recorded. The crossing has become so popular that congestion sometimes develops, with some drivers reporting hours-long waits during peak periods. But for most users, the ability to cross the Pearl River estuary in half an hour instead of 2 hours represents a transformation in regional connectivity. The Shenzhen-Zhongshan link is part of a broader strategy to integrate the Guangdong-Hong Kong-Macau Greater Bay Area, a region covering 56,000 square kilometers with a population exceeding 70 million people. The area generated economic output of over 14 trillion yuan, approximately $1.1 $1.96 trillion in 2023. China aims to develop it into a world-class city cluster and global technology center. At $4.83 billion and 24 kilometers long, with a tunnel that accounts for nearly 7 kilometers of underwater passage, the Shenzhen-Zhongshan link demonstrates how modern engineering can overcome geography that once seemed impassable. But even this ambitious project pales in comparison to what comes next. Our next bridge doesn't cross the widest river or dive the deepest underwater. Instead, it conquers something engineers once considered impossible, spanning a river valley using only a single tower on one side. And it does this in one of the most remote and mountainous regions of China, where the construction site itself sits 320 meters above the assembly yard below. Moving from the coastal plains of Guangdong to the rugged mountains of Yunnan province, we encounter a bridge that breaks every conventional rule of suspension bridge design. The Liujijiang Bridge, which opened in April 2022, is the world's first single-tower, single-span suspension bridge, a structure that physics textbooks once suggested was impossible. The bridge stretches 798 meters across a V-shaped canyon carved by the Liujijiang River, whose name translates literally as Green Juice River. The main span between the tower and the opposite mountainside anchoring point measures 780 meters, surpassing the previous single-tower record of 766 meters held by the Jinshajiang-Hutia-Oxia Expressway Bridge. But the span measurement doesn't capture what makes this bridge extraordinary. Traditional suspension bridges use towers on both sides of the gap, with cables draped between them supporting the deck. The Liujijiang Bridge uses only one tower on one side, with the cables anchored directly into the mountain on the opposite side. There are no additional support columns anywhere. The entire 798-meter length hangs in space, supported by cables attached to a single tower and a tunnel anchorage carved deep into solid rock. The bridge is located in central Yunnan province, connecting Yuxi City and the Chuxiongyi Autonomous Prefecture. Before the bridge opened, crossing from one side of the valley to the other required a 1.5-hour journey through winding mountain roads. The Liujijiang Bridge reduces that journey to 2 minutes, with vehicles traveling across at speeds up to 100 kilometers per hour. Construction began in 2019 and took 3 years to complete, a relatively short timeline for such an innovative structure. But every phase of construction presented challenges that had never been faced before. The most immediate problem was the terrain itself. The bridge is built in a V-shaped canyon with near-vertical cliffs on both sides. The bridge deck sits 320 meters above the valley floor, where the construction assembly yard had to be located. That's equivalent to a 100-story building. Getting materials and equipment up those cliffs required building temporary access roads carved into rock faces so steep that trucks could barely navigate them. The single tower rises 156 meters from its foundation and stands on a steep mountainside rather than flat ground. Every component of the tower had to be transported up the mountain and assembled piece by piece in a location where there was barely room to maneuver equipment. Workers operated at heights and angles that would be considered extreme, even by mountaineering standards. The opposite side of the canyon presented an even greater challenge. Without a tower on that side, the main cables must be anchored into the mountain itself. Engineers designed what they claim is the world's steepest tunnel anchorage, carved into solid rock at an angle of 54 degrees. The tunnel extends deep into the mountain, with the cables splayed out inside and locked into massive concrete anchor blocks that transfer the pulling forces into the surrounding bedrock. The steel box girder deck weighs approximately 10,000 tons, equivalent to the weight of the Eiffel Tower. This entire mass hangs from cables attached to the single tower, creating enormous stress concentrations. The tower must resist not only the downward force of the deck's weight, but also the horizontal pulling forces from the cables. To handle these forces, the tower is built from reinforced concrete with a carefully designed cross-section that distributes stress evenly. The foundation extends deep into the mountainside, with dozens of piles drilled into bedrock to anchor the tower against the pulling forces that try to topple it. The deck consists of 61 prefabricated steel box girder segments, each manufactured in the valley below and then hoisted up to the bridge level. The maximum weight of a single segment exceeds 180 tons. Lifting these massive steel sections 320 meters vertically required specialized cranes and rigging systems designed specifically for this project. On March 9, 2022, workers installed the final deck segment, completing the closure of the bridge. This was a critical moment. If the two ends of the deck meeting in the middle didn't align within a few millimeters, the entire structure would need adjustment. The precision achieved after 3 years of construction in one of the most challenging environments in China was a testament to careful planning and skilled execution. The bridge emerges from tunnels on both sides of the canyon, adding to its dramatic appearance. Vehicles approaching from either direction drive through a mountain tunnel, then suddenly burst into open air high above a river valley with nothing but sky and mountains visible ahead. The tunnel-to-bridge transitions were carefully designed to prevent drivers from being suddenly blinded by sunlight after the darkness of the tunnels. The Liujiang Bridge is part of the 190-kilometer Yuchu Expressway, which connects Yunnan to other major national highways, including the Hangzhou-Ruili Expressway running to a city on the Myanmar border, and the Guangzhou-Kunming Expressway linking the coast to the interior. The bridge is also a critical component of Yunnan's 9,000-kilometer provincial highway network. Neither Yuxi City nor the Chuxiongyi Autonomous Prefecture are major tourist destinations, but they sit in the heart of Yunnan province between major cities like Kunming and Dali. The improved connectivity is expected to promote tourism development and economic growth in central Yunnan, giving local agricultural products faster access to urban markets and reducing the isolation that has historically limited development in the region. Project manager told Chinese state media that the height difference between the bridge deck and the assembly yard is 320 meters high, or about 100 stories high. The complexity of this project is rarely seen in China. For a country that has built dozens of the world's highest and longest bridges, this is a significant statement. The single-tower design offers several advantages beyond just the engineering challenge it represents. In deep V-shaped valleys like the Liujiang Canyon, building towers on both sides can be prohibitively expensive because of the difficult terrain. A single-tower design reduces the amount of work needed on one side of the canyon, cutting construction costs and time while still achieving the necessary span. The bridge also had to withstand the region's environmental conditions. Yunnan province experiences significant temperature variations between seasons, strong winds funneling through mountain valleys, and occasional seismic activity. The bridge was designed to handle all of these forces while maintaining enough flexibility to prevent damage from thermal expansion and contraction. After completion, the Liujiang Bridge quickly became recognized as an engineering marvel, attracting international attention despite its remote location. The bridge demonstrates that when conventional engineering solutions won't work, innovation can create entirely new approaches that become the foundation for future projects. The Liujiang Bridge represents the cutting edge of suspension bridge design, a structure that exists only because engineers were willing to challenge the assumption that you need towers on both sides. But remarkable as this 798-meter single-tower span is, it's only number 5 on our list. The next bridge on our countdown doesn't break records for height or innovative design. Instead, it shatters the concept of what a bridge even means by stretching so far that it becomes its own kind of landscape, a structure so long that trains traveling across it at 300 kilometers per hour still need more than half an hour to complete the crossing. From a bridge suspended from a single tower over a mountain valley, we now travel to the fertile lowlands of Jiangsu Province, where engineers have built something that redefines the very concept of a bridge. The Danyang-Kunshan Grand Bridge isn't just the longest bridge in the world, it's the longest structure of any kind ever built by humans, stretching an almost incomprehensible 164.8 kilometers. To put this in perspective, that's longer than the distance from Modena to Milan in Italy. It's longer than the width of many small countries. If you place this bridge in the United States, it would stretch from downtown Philadelphia well past Trenton, New Jersey, and the entire structure is elevated 30 meters above the ground, carrying high-speed trains at 300 kilometers per hour. The Danyang-Kunshan Grand Bridge opened in June 2011 as part of the Beijing-Shanghai High-Speed Railway, one of the most important transportation corridors in China. It connects Shanghai, the largest city in China with a population exceeding 24 million, to Nanjing, the capital of Jiangsu Province. The bridge runs through several major urban areas, including Danyang, Changzhou, Wuxi, Suzhou, and Kunshan, cities that are home to tens of millions of people combined. Construction began in 2006 and was completed in just 4 years, an astonishing timeline given the scale. The project employed 10,000 workers simultaneously at various points along the route, working in coordinated teams to build what amounts to a continuous viaduct nearly 165 kilometers long. The total cost was $8.5 billion, which breaks down to approximately $51 million per kilometer. The bridge consists of approximately 2,000 individual spans, each around 80 meters long. The structure is built as a viaduct, a segmented bridge made of smaller sections held up by piers and arches. About 9,500 concrete piers support the entire length, with 450,000 tons of steel used in the construction of the deck and support structures. Why build such an enormous elevated structure instead of laying tracks on the ground? The answer involves economics, geography, and practicality. Building a conventional railway line through this region would have required approximately 70 acres of land that would need to be acquired from farms, towns, and cities along the route. The elevated viaduct requires only 27 acres per kilometer, saving enormous amounts of valuable land in one of China's most densely populated regions. The terrain itself posed significant challenges. The Yangtze River Delta region is characterized by soft soil, wetlands, rice paddies, rivers, canals, and lakes. These conditions make building conventional foundations extremely difficult. An elevated viaduct solves these problems by lifting the entire railway above the problematic terrain, with piers driven deep into bedrock beneath the soft surface layers. The bridge also crosses approximately 150 river channels and waterways along its route. A 9-kilometer section spans the open waters of Yangcheng Lake in Suzhou, with 200 piers built in the lake to support this portion. For most of its length, the bridge follows parallel to the Yangtze River at distances varying between 8 and 80 kilometers to the south. The design incorporates both cable-stayed sections for longer spans and simple beam sections for shorter distances. This hybrid approach allows engineers to adapt the structure to different terrain and obstacles along the route without maintaining a single consistent design for the entire 165 kilometers. The flexibility of the design was key to completing such an ambitious project on schedule. Building a structure this long required accounting for Earth's curvature, over 164.8 kilometers. The curvature of the planet causes a measurable deviation from a perfectly straight line. Engineers used geodetic surveys and Earth radius calculations to adjust the elevation and alignment of different sections, ensuring trains could travel smoothly without encountering sudden grade changes or alignment issues. This level of precision over such distances represents a remarkable achievement in surveying and construction control. The bridge is designed to withstand magnitude 8 earthquakes, typhoons with sustained winds over 100 kilometers per hour, and impacts from naval vessels up to 300,000 tons, roughly equivalent to the largest cargo ships in the world. Each pier is equipped with elastomeric bearings and sliding plates that can absorb seismic shocks and allow the structure to flex during earthquakes without sustaining damage. Temperature presents another challenge for a structure this long. Steel and concrete expand when heated and contract when cooled. Over 164.8 kilometers, even modest temperature changes can cause expansion and contraction of several meters. The bridge design incorporates expansion joints at regular intervals that allow sections to move independently, preventing stress buildup that could damage the structure. The maximum clearance beneath the bridge is 150 meters in some sections, high enough for large cargo ships to pass beneath when the bridge crosses major navigation channels. Most of the bridge maintains an average height of 30 meters above ground level, high enough to cross local roads, railways, and waterways without interfering with ground-level traffic. The impact of the Danyang-Kunshan Grand Bridge on regional transportation has been transformative. Before its construction, the journey from Beijing to Shanghai took 18 hours by conventional train. The high-speed railway, including this bridge as its longest continuous section, reduced that journey to less than 5 hours. Similarly, the trip from Ningbo to Jiaxing, which previously took 4.5 hours because of the need to navigate around lakes and rivers, now takes just 2 hours. This time, savings translates directly into economic benefits. Business travelers can make same-day trips between cities that once required overnight stays. Agricultural products from the fertile Yangtze Delta can reach markets faster. The industrial cities along the route have better access to labor pools and supply chains. The bridge has become a critical artery in one of the world's most economically productive regions. The construction process involved prefabricating most bridge segments in factories along the route, then transporting them to the installation site and lifting them into place with specialized equipment. This approach reduced disruption to the communities below and allowed for better quality control than would be possible with entirely on-site construction. Each prefabricated segment was precisely manufactured to match the calculated dimensions for its specific location along the bridge. During construction, engineers paid careful attention to environmental impacts. The bridge crosses sensitive lake ecosystems and agricultural land. Pier placements were adjusted to minimize disruption to aquatic life and soil displacement. The elevated design prevents the railway from fragmenting habitats and allows wildlife to move freely beneath the structure. The Danyang-Kunshan Grand Bridge holds the Guinness World Record for the longest bridge in the world, a title it has held since opening in 2011. Remarkably, the same Beijing-Shanghai high-speed railway includes 2 other bridges in the top 10 longest bridges in the world: the Langfang-Qingxian Viaduct at 114 kilometers and the Tianjin Grand Bridge at 113 kilometers. This concentration of extremely long bridges on a single railway line demonstrates China's commitment to infrastructure development in the 2000s and 2010s. The country transformed its construction capabilities to the point where building 100-kilometer-long elevated railways became routine rather than exceptional. Passengers traveling on trains crossing the Danyang-Kunshan Grand Bridge don't see a dramatic landscape of soaring heights or deep valleys. Instead, they see rice paddies, rivers, lakes, and urban areas passing beneath at high speed. The bridge is so long that most passengers crossing it don't even realize they're on a single continuous structure. It simply becomes part of the landscape of the journey from Shanghai to Nanjing. The bridge requires continuous maintenance to keep it in service. Inspection crews regularly check every pier, every segment, every joint for signs of wear or damage. The sheer length of the structure means maintenance is a never-ending process. By the time crews finish inspecting one end, it's time to start again at the other end. This proactive maintenance ensures the bridge continues to perform safely despite carrying thousands of high-speed trains every week. At 164.8 kilometers long, the Danyang-Kunshan Grand Bridge represents the ultimate expression of the viaduct concept, a structure so extensive it becomes its own geographic feature. The final 3 bridges on our list represent different engineering philosophies, each pushing boundaries in their own way. At number 3, we arrive at the Chiming Three Provinces Bridge, better known as the Jiming Bridge, which opened in January 2020 at one of the most remote and historically significant locations in southwestern China. The bridge spans the Qishui River at a point where 3 provinces, Sichuan, Yunnan, and Guizhou, meet. The location gets its name from a Chinese saying: "In the past, when a rooster crowed in the morning, the sound could be heard across all 3 provinces." But that proximity was deceptive. The steep canyon carved by the Qishui River meant that traveling from one side to the other required a journey of more than 2 hours through dangerous mountain roads and a ferry crossing. The Jiming Bridge reduces that journey to 2 minutes. The arch bridge stretches 286.4 meters across the canyon, with a main span of 180 meters and a height of 162 meters above the river. The structure is 11.5 meters wide, carrying 2 lanes of traffic plus sidewalks on both sides. What makes this bridge remarkable isn't just its technical specifications, it's the transformation it represents for one of China's most isolated regions. The area is home to 12 townships across 8 counties. places where poverty and isolation have been facts of life for generations. Before the bridge, farmers carrying baskets of plums from the Sichuan side to markets in Yunnan would begin their journey 2 days early. They'd walk down the mountain, cross the river by ferry, climb back up the mountain on the opposite side, sleeping on the roadside along the way. After reaching county markets, they could sell their plums for 0.5 yuan per kilogram, barely enough to cover the journey's costs. Construction took 3 years, from 2017 to 2020, and cost 59 million yuan, split equally between Shuyang County in Sichuan and Zhenjiang County in Yunnan. The project employed workers who lived on site in one of the most challenging construction environments in China. The bridge site was so remote that during winter, ice made the mountain roads impassable to trucks. Materials had to be transported during favorable weather and stockpiled for months. Workers crossing between the two construction sites didn't have the luxury of a bridge. They rode in a suspended cable car, welded from iron sheets and steel bars, rattling across the 310-meter span in about 20 minutes. The first person to ride this contraption, a clerk from Sichuan, called the foreman to make sure it was safe. He later joked that if the cage did fall, at least the drop wouldn't last long. The crane operators, a married couple named Zhang Chunhua and Chen Shijun, worked at the highest points of the construction site, 256 meters above the water. Zhang's husband taught her to operate the tower crane when she was 30. The first time she climbed up behind him, the structure shook and she was too frightened to move. By the end of construction, she faced that 256-meter drop every day and felt numb to it. The Qishui River itself holds historical significance. It's known as the River of Wines because several famous Chinese spirits, including Mao Tai, are produced along its banks. The river's distinctive reddish color comes from sediment concentration, giving it the name that translates to Red Water River. It was also the site of a major battle during Mao Zedong's Long March in 1935. The arch design was chosen for both aesthetic and practical reasons. Arch bridges can span longer distances than simple beam bridges while using less material than cable-stayed or suspension bridges. For this remote location where every ton of material had to be transported through treacherous mountain roads, efficiency mattered. The Jiming Bridge also serves as a gateway to tourist attractions. A cliff walk on the Sichuan side, more than 200 meters above the river, carved by villagers over 10 years using hand tools, is now accessible to visitors from all 3 provinces. What was once a desperate route to market has become a tourist destination, and the bridge makes it reachable. When the bridge opened to traffic on January 21, 2020, project manager Jiang Zhongqiao told reporters, "We spent 3 years building the bridge, and I am glad that it is finally open to traffic." For the approximately 12 townships and 8 counties in the region, the bridge represents more than infrastructure. It's an economic lifeline connecting communities that geography had separated for thousands of years. Yet, at 180 meters of span and 162 meters of height, the Jiming Bridge is modest compared to number 2, a bridge connecting not just provinces but entire regions, and transforming not just isolated communities, but some of the world's most economically important areas. While the Jiming Bridge connects remote mountain communities, the Hong Kong-Zhuhai-Macau Bridge connects 3 of the most economically dynamic cities in Asia. At 55 kilometers long, it's the longest sea crossing system in the world and one of the most complex engineering projects ever completed. The bridge opened in October 2018 after 9 years of construction, linking Hong Kong, Zhuhai, and Macau across the Pearl River estuary. Before this bridge, traveling by road from Hong Kong to the other 2 cities required a 4-hour journey around the estuary. The bridge reduces that to just 45 minutes, fundamentally reshaping the Pearl River Delta's economic geography. The structure isn't a single continuous bridge. It's an integrated system consisting of 3 cable-stayed bridges, a 6.7-kilometer undersea tunnel, and 4 artificial islands. This combination was necessary because the Pearl River estuary is one of the world's busiest shipping channels, and a bridge stretching the entire distance would obstruct navigation. The 3 cable-stayed bridges span the shallowest sections of the estuary, with their navigation clearances allowing ships to pass beneath. The longest of these, The Qingzhou Channel Bridge has a main span of 458 meters and towers rising 163 meters above the water. These bridges alone would be considered major achievements, but they're just components of the larger system. The artificial islands serve as transition points where the bridge dives underwater. These islands, built using giant steel cylinders driven into the seabed and filled with sand, had to be constructed in water depths exceeding 40 meters with strong currents and frequent typhoons. Each island covers an area equivalent to several football fields and houses ventilation equipment for the tunnel sections. The 6.7-kilometer undersea tunnel consists of 33 immersed tube sections, each 180 meters long and weighing 80,000 tons. These were prefabricated on land, floated to the installation site, and sunk into a pre-dredged trench on the seabed. The precision required was extraordinary. If the sections didn't align within millimeters, water would leak into the tunnel. The tunnel section was necessary for a specific reason. Hong Kong International Airport sits directly above part of the crossing route. A bridge would interfere with aircraft flight paths, so engineers designed the tunnel to pass beneath the airport approach lanes, maintaining aviation safety while creating the crossing. Construction faced challenges unprecedented in bridge engineering. The Pearl River estuary experiences typhoons regularly, with waves that can exceed 10 meters in height. The structure had to withstand magnitude 8 earthquakes, ship collisions from vessels up to 300,000 tons, and temperature variations that cause expansion and contraction across the entire 55-kilometer length. The bridge cost approximately about $17 billion, making it one of the most expensive infrastructure projects in history. The investment reflects not just the technical challenges, but the strategic importance of connecting the Guangdong, Hong Kong, Macau Greater Bay Area, a region with a population exceeding 70 million and an economy larger than most countries. The structure carries 6 lanes of traffic, with a speed limit of 100 kilometers per hour. Since opening, it has dramatically increased the flow of people and goods between the 3 cities, enabling same-day business trips that were previously impossible, and integrating labor markets and supply chains across the region. The Hong Kong-Zhuhai-Macau Bridge represents a different kind of ambition than mountain-spanning suspension bridges or record-breaking arch bridges. Its infrastructure is an economic strategy, a physical manifestation of China's goal to develop the Pearl River Delta. At 55 kilometers and $17 billion, it's the longest and one of the most expensive sea crossings ever built. Our final bridge combines technical innovation with a different kind of record. It is the longest arch bridge in the world, pushing a 2,000-year-old design concept to its absolute limit. We end our journey where we began, in Guangxi Province in southern China, with a bridge that represents the pinnacle of one of humanity's oldest structural forms. The tian'e Longtan Bridge, which opened to traffic in 2023, became the world's longest arch bridge with a main span of 600 meters, a distance that engineers once thought impossible for this type of structure. Arch bridges are among the oldest designs in human history. The Romans built stone arches that still stand 2,000 years later. But arch design has a fundamental limitation. The longer you make the span, the more the compression forces multiply exponentially. At 600 meters, the tian'e Longtan Bridge faces forces that would crush traditional materials instantly. To overcome these physics-defying challenges, Chinese engineers used a basket arch design constructed from high-strength steel tubes filled with concrete. This hybrid approach provides the compressive strength of concrete with the flexibility of steel, creating a structure that can handle enormous forces while absorbing vibrations from traffic and wind. The bridge is located in Guangxi's mountainous terrain, where deep river valleys have historically isolated communities. The Longtan Bridge crosses the Longtan Reservoir at a location where the gap between mountains measures 600 meters. Building traditional foundations on both sides and connecting them with any design besides an arch would have cost far more and taken much longer. The construction process required extraordinary precision. Workers erected temporary support structures in the middle of the reservoir, 200 meters above the water, just to hold the arch segments during assembly. If the two halves of the arch meeting in the middle were misaligned by even a few centimeters, the entire structure would be compromised. Temperature was another challenge. Across 600 meters, even modest temperature changes caused the steel to expand or contract by several centimeters. Engineers timed the final connection for the exact moment when temperatures were optimal, ensuring perfect alignment. The bridge cost approximately 1.6 billion yuan and took 5 years to complete. For that investment, China achieved more than a world record. They proved that the 500-meter barrier for arch bridges could be broken, and that ancient structural principles could be pushed to new extremes with modern materials and techniques. For the approximately 160,000 people living in the surrounding counties, the bridge transforms geography that has shaped settlement patterns for millennia. Communities separated by hours of mountain roads are now minutes apart. Agricultural products reach markets before spoiling. Medical facilities become accessible to entire regions. But the Tian'e Bridge represents something beyond local impact. At 600 meters, it demonstrates that even the most thoroughly understood engineering principles still have room for innovation. The Romans would recognize the arch design, but the scale and materials would seem like magic to them. From arch bridges to suspension bridges, cable-stayed bridges to undersea tunnels, China is truly testing the limit. If you enjoyed this video, keep following Signum for even more insane stories from the world of